Well, welcome everyone to the Dean's Lecture. That sounds so like pretentious when I say Dean's Lecture, because it's my title. I'm Kyung Lee, I'm the Dean of School of Engineering. So thank you for coming and joining us for a wonderful occasion. Before I start introducing our honored speaker, I have a few housekeeping items that it's now my job to do. Usually Dean Swan would be doing this, so I have some big shoes to fill. I hope he doesn't hear about it and let me know after he comes back that I've let him down. So, some housekeeping items. We ask that you silence your phones and please do not use flash when taking pictures. You're welcome to use your phones to take pictures, but don't use flash. Also, I want to let you know that the event's being recorded, and they will be posting the event talk online at a later date. And I hope, Dean Abramson, that someone has already checked with you. That's okay. Terrific. Okay, so let's get started. Over the years, we've welcomed many guest speakers to campus to give this lecture. Trailblazers in the field. We had the pleasure of welcoming an astronaut, CEO of a multinational company, humanitarians, engineers who developed 3D printing. And today's speaker is no different. We have another trailblazer as a guest to speak to us about her work. So my job is not to take up too much of her time, is to make sure that I have a brief introduction, although that's going to be difficult because she has many accomplishments to her credit, some of which are actually not even in her bio, but I learned over a very enjoyable Boston traffic ride to dinner together. So I'm very delighted to welcome Alexis Abramson. She's an alum, Dean and Professor of Engineering at Dartmouth College, and she's going to talk to us about the contribution of buildings to the clean energy transition, which focuses on the need to cut carbon emissions, particularly in the building sector, which accounts for over 40% of energy used in the US and EU. Electrification, fueled by advances in heat pump technology and policy incentives, remain critical despite rising energy demands. Her presentations can explore these challenges and opportunities in addressing climate change through this work. She is the 13th Dean of the Thayer School of Engineering at Dartmouth, where she has been since 2019. At Dartmouth, she is in the midst of a growth of the school, putting human-centered engineering at the heart of the education experience for their students, as well as research and engineering practice. Dr. Abramson's research has focused on thermal transport, and I know how much she loves thermal, from designing nanostructured materials to addressing building energy efficiency. And as I learned yesterday, she is helped me breathe as I drive through the Big Dig. So thank God, if she wants, she can talk more about it. But it was fascinating work, and now I know what's behind the walls in the tunnels. So a bit of a little mystery teaser for you. As an academic, she's also co-founded Edifice Analytics, a startup that conducts virtual energy audits and manages building optimization. Before she joined Dartmouth, she was the Maltz Professor of Energy Innovation at Case Western Reserve University in Cleveland, and served as a director of the university's Great Lakes Energy Institute. During the Obama administration, Dean Abramson had the role of chief scientist and manager of the Emerging Technologies Division at the US Department of Energy, its Building Technologies program. And in 2018, she also served as a technical advisor for Breakthrough Energy Ventures, a billion-dollar effort launched by Bill Gates to combat human-driven climate change. She received a BS and MS from Tufts Mechanical Engineering. She's a double jumbo. Her PhD from the University of California, Berkeley. Please join me in giving Dean Abramson a warm jumbo welcome.
Thank you. Well, thank you. Thank you, Dean Lee, for inviting me to be here and to be back. I've come back a little bit over the last 30 years or so, but just am so amazed by just how different it actually is, and things that I didn't know I remembered are coming back to me. Like I started talking about ES7, which is what thermodynamics was called. I didn't know that I remembered that. But, you know, one of the reasons why, or I might even say the reason why I chose to come to Tufts as an undergrad and study engineering was because I wanted this experience of engineering integrated with the liberal arts. Because I knew that I wanted to be the kind of engineer that was more human-centered, that was more holistically trained, right? I wanted to be able to use my experience in the pottery class I took downtown at the art school, to the economics class that I took, to the philosophy class, and use those learnings as I was learning about engineering and integrating that in. And one of my favorite memories of Tufts is I took a history of women class from a very famous historian, and was so excited to be in that class. And we had to write a paper, and I chose to write a paper about the history of working women, and I compared that to an undamped oscillator. And you know, I thought this was a really great analogy for those of you who know what an undamped oscillator is. I'm not sure that my history professor had as much appreciation for it as I did, but I think it really kind of captured my love of learning and that integration of STEM and humanities and the arts and bringing it all together. So I'm really proud to be a double jumbo. So today I'm going to talk to you about climate change and energy and building efficiency in particular. As you heard, sort of that's been a background that I've developed over the years. And hopefully leave you today with a different appreciation of the role of buildings, and maybe even thinking about what you can do either in your future careers if you're a student, or what you might do to really impact energy and energy efficient buildings in your own lives. So let's think about where are we today. So where are Americans today? This is how we use energy. And a quadrillion BTUs is a measure of energy, right? Don't worry too much about the units, but in the US we use about 100 quads or quadrillion BTUs of energy. And it's across really 4 sectors if you want to kind of simplify it, right? We've got transportation, the industrial sector, like usage of different forms of energy to create plastics and steel and all these other things that get integrated into components in our lives. And then about 40% total is residential buildings plus commercial buildings. So your homes plus the businesses, or this would be considered a commercial building. So that's about 40%, those two added together. And if you look at it from the standpoint of electricity, and we're going to talk about this a bit, to really move forward in terms of having as much impact on mitigating climate change in buildings as we can, we need to think about electrifying everything. You might have heard that term before, right? This idea that if we can start generating electricity with renewables, could be solar, it could be wind, it could be even nuclear, so clean electricity. If we can generate more and more electricity cleanly, then we're going to need to start to make sure that these different sectors run on electricity more. And if you look, I put on here the percentage of that energy consumption today that is electric. So this is today. So residential, so 40% of the energy consumption in your homes comes from the wires that are connected to your houses. It's about the same in commercial. It's a lot less in industrial. And certainly, even though you see a lot of electric cars out there, right, really, it's really not very big. It's still just about 1% or less of the transportation industry, because we're talking not just cars, but we're talking trucks and buses and all of that. About 1% or less is actually using electricity today. And if we kind of dig in a little bit more, what this is showing you is a map of the US, And specifically heating, right? You think, well, what are the other forms of energy that are being used in buildings? Well, if it's not electricity, you're burning fossil fuels. I'm sure many of you use natural gas, right, to burn actually in your homes, and that natural gas burning, right, releases carbon dioxide into the atmosphere, which then leads to climate change. And in fact, when you think about heating in particular, about 70% of the homes in the US are burning fossil fuels in the home, are burning fossil fuels and releasing that into the environment. So if we believe this premise that we need to electrify everything, right, we need to move from this kind of 40% or so electrification in our buildings to 100% or so of electrification in our buildings, gosh, somehow we're going to have to take that 70% of the fossil fuel burning, and we're going to have to turn that into all electric, right? And that is an immense challenge. Also, what else inside of a building, a home, burns fossil fuel directly? Your water heaters. If you've got gas heating in your home that you're burning to heat, you're probably burning it to heat your water as well. You probably have some cooktops, right? And you probably have gas, natural gas coming in for that. Tends to be a small percentage of the total energy use, but still. And all of that is going to have to turn electric in order for us, and be clean electric in order for us to stop releasing CO2 into the atmosphere. I'll just go back. We're going to focus more on the building side, but look at the huge challenge we would have in industrial, right? At 17%, it's actually really hard in the industrial sector to move from burning fossil fuels to electric. A lot of that has to do with high temperatures that are needed in order to achieve some industrial processes. Transportation, we're on our way. You see a lot of companies out there that sell electric cars, right? There's a lot more interest from consumers into electric vehicles, but having the impact on the aviation industry, on buses, on shipping, on all of that, that's going to take some time. So we still have a lot in front of us in order to get to this point where we're able to electrify everything. And I should also mention too, right, now where the building, your home, you were concerned about heating, water heating, space heating, maybe some cooking, burning fuels. Well, now you're actually plugging in your vehicle. So a place, the home, which didn't have a high electricity load, now all of a sudden does. So we've got to think about this. We've got to think about, okay, if electrifying everything is the way to go, right? There are lots of great, smart people thinking about how to get more solar and wind and nuclear and hydro on the grid. That's great. Some of that's centralized. Some of that will be distributed. That's great. Now, we, building people, have to think about what could that look like? When we think about the deployment of various different technologies that influence the building industry, the costs, the policies associated with all of those things, right? Kind of how might things look? How might things change into the future? And so one model, there are many out there, kind of is predicting how this electrification will change over time. And if you recall what we had a few slides ago, right, we were closer to about 40%. This particular model predicts in 2050, we'll be closer to about 63% of buildings being electrified. At some point, we still really need to get to 100 in order to stop burning fossil fuels. We'll make some progress on the industrial side. The transportation industry, perhaps not surprisingly, you'll see the biggest jump in transportation. There's a lot of momentum there. What you'll also see is energy efficiency. So hopefully the whole circle gets smaller because we're able to make the technologies that we're using inside our buildings much more efficient. We've seen this happen over years. If you look at the energy use in buildings per square foot, it actually has gone down. We've added some things like electric vehicle charging that kind of might make it look like it's going up, but it's for the most part gone down over the years because of efficiency. A refrigerator that was built and installed in the 1970s, 1980s is about 5 times worse for the environment than one today. And so if you know anybody hanging on to those old refrigerators, you can run the numbers. I believe everybody in this room could. You could run the numbers to really look at what kind of savings there would be if you just were to replace it with a new technology today. Okay, so for buildings, this, again, largely means space and water heating, and there's just a nice little picture here kind of showing the relative size of that energy usage. It should be no surprise space heating itself is the biggest consumer of energy, right? Now, of course, that is dependent where you live. And all of you should understand, and if you don't, I want you to think about it and absorb this, right? The greater the difference in temperature between the outside and what you want the inside to be, the more energy it's going to take to reach that temperature on the inside. So in a place like Boston, or where I am, Hanover, New Hampshire, where it's about 10 degrees colder than what it is here usually, right? It takes a lot of energy to actually heat the buildings that we're in. As you get it to warmer and warmer climates, right, it takes less and less energy to do that. And again, most of that energy is coming from fossil fuels. You see space cooling, sometimes people are surprised, right? This is just on average over in the US, but space cooling is only 12% because what I just said, remember, when the temperature difference between the outside and the inside is large, you're going to use larger amounts of energy. Really, if we're talking about 85 degrees, I'll use Fahrenheit, outside, right, and we want it to be, 72 degrees, that's only a 13-degree difference. When we're talking about heating, well, you might be talking about 30 degrees Fahrenheit on a good day in Boston in the middle of winter. You still want it to be, 65 degrees inside. That's 35 degrees difference. So that is largely why our space heating is so much larger than our cooling. The thing is about cooling, though, it's already electric. You rarely find any other forms of generating energy to cool a space. So it's already electric, so that's good. But now when I add my space heating plus even my water heating together, right, this, relatively speaking, those are the two areas where the greatest consumption of energy is, and those are the two areas where the greatest consumption of fossil fuel burning energy also is. And then I mentioned too, also we have to think about electric vehicles. This is a graph of how much energy electric vehicles are expected to use over time. So this is a projection, right? And there's a high case, a reference case, and a low case, depending on the assumptions you're making in that model, right? And so that is going to go up significantly over time. And so if you think about that, again, you're going to start paying a lot more on your electricity bill as we move in this direction. So we've got to replace our fossil fuel burning furnaces with something electric. Is this what we're talking about? How many of you in the audience either have this sort of in your home, something that looks like this, or have been in somebody's home where you've seen something that looks like this? Yeah, right? These typically are electric baseboards, right? And they really are electric, and you think, oh, well, that's great because we're moving toward electrification, and hopefully the electricity that's feeding that electric baseboard there, hopefully that's coming from some solar power somewhere, and so it's green electricity. Okay, maybe that's okay, but actually that's not what we're talking about here. right? So we're in 2024. I think we can move past the 1970s baseboard heaters. And instead, what we're moving to are heat pumps. And it's a wonderful technology and for a variety of different reasons. One thing is that a heat pump, electrically driven, can both heat and cool. And this is a diagram here of when we're in the winter and when we're in the summer. And really all you have to do is turn the refrigerant, the working fluid, in one direction to be able to heat and the other direction to be able to cool. So you can use one system for your heating and your cooling. And for those of you who maybe are studying mechanical engineering, right, you know, right, this is a standard refrigeration or air conditioning cooling cycle with you've got your compressor and your condenser and your evaporator. And again, all you're doing is using this refrigerant to move it through this cycle. I won't go into thermodynamics, even though I really want to, but I won't. To really, either if it's the middle of winter, no matter what the outdoor temperature is here, this refrigerant is colder than that. And so this refrigerant actually absorbs the heat from 30-degree weather. It's absorbing the heat because this is at 20 degrees. And so it's absorbing the heat and bringing that through the process and then dumping that to the inside once it gets heated up a little bit more, but dumping that to the inside of the house to heat the house. And the same thing happens, those of you I'm sure have had window air conditioners at some point, right? And actually what's happening is the air inside the house is running through the air conditioning system. The heat is being drawn out and that's being kicked out into the outside, which is at a hotter temperature. So that is a way then to kind of grab heat, which is existing in the atmosphere, and use it to actually heat, or if it were the other direction, cool the space. So it's a very efficient process. And in fact, it could be 2 to 4.5 times the efficiency of a gas furnace when we're talking about heating. So it's much more efficient than your typical gas furnace, and it's electric. And so again, hopefully we've got some solar panels, some wind, some nuclear, some hydro, what have you, generating that electricity and now being used to run this very efficient heat pump. And what has been a phenomenal improvement in the industry is the ability to operate a heat pump in cold climates. So in Hanover, New Hampshire, in my house, we have a heat pump that both heats and cools. And I'll show you a picture of the house in a bit. But it used to be really challenging to actually get the refrigerant to be cold enough such that you could actually absorb heat at very low temperatures outside. And now we're able to do that. Some improvements in the compressor, in the refrigerants that were used, are now making it much more viable and relatively inexpensive to put a heat pump for heating purposes in the coldest parts of the year. And when you think about it, right, at the end of the day, putting one system in, well, that's cheaper than putting two systems in. This is just a picture of sort of the energy consumption in a building under 4 different conditions. So this is a building without air conditioning, with your typical air conditioning, with high capacity, so even high efficiency air conditioning, but then one with a heat pump that does both heating and cooling. And so, the light gray bars here actually are kind of the electricity or gas cost, depending on what's in the home, to just run everything in the home. And then the heating and cooling is everything above it. So you see it's about 50% or so is used for heating and cooling. And so obviously if you have no air conditioning, right, you're not paying for that, the light blue. If you have a typical air conditioning system, then this is, and I think this is the average home in the US, then you're paying, something for heating, a lot for heating, because again, you got a big delta T, a big temperature difference, and you're paying something for cooling. Great, you want to put a more efficient system in, that's great, that helps you, but then if you put in a single system that does heating and cooling with just that reversing valve on it, then the operational costs of your energy each year is much less. And this adds up, obviously, over time. Okay, so I've just described to you this wonderful future ahead of us of how we're going to electrify everything, and it's all going to work out. We've, of course, got to hope that and strategize and plan and put policies in place and think about economics and make sure the technologies are there to make all those energy generation sources clean and green. But we also have a problem because most of what I've shown you so far is the average for the US. And as you know, right, we can't just treat every problem as an average, especially when you look at some of the outliers and how you might treat those outliers differently. So what this graph actually is, a graph of the US, and on the coldest days of the year, so I don't know, what was the coldest winter day, would you say, this year? It wasn't that cold this year, but it got Fahrenheit below 0 at some point, right? That's pretty cold, right? So, and those days happen maybe 5 days a year, let's just say in Boston. I didn't look this up. I'm just guessing, like below 0 in Boston for a appreciable amount of time, let's just say about 5 days a year. And you put in a heat pump, let's say to operate the heating in this building. Well, that heat pump can operate, and let's say we size it appropriately so that even on those 5 coldest days a year, that we're going to be able to meet the needs of this space, but we're going to have to run that heat pump 24/7, right? We've sized it such that it's got to work its hardest on the coldest days of the year. And it's not just this building, but it's every building on campus. And it's every house in the area. And it's every commercial building in Boston. And it's everywhere. And when you kind of run the numbers for, again, we're talking 5 days a year, you kind of have to build a grid that's going to be able to handle that. And that grid would have to be able to supply about 4 times the electricity needed just for those 5 days a year. The other days, it would obviously be less than that, but 4 times the sort of average heating day. And that's just impossible, right? We're already having a hard enough time being able to make sure there's enough wind and solar and hydro and nuclear, et cetera, to be able to just meet sort of the typical load that will be needed when we electrify everything. And so what do, right? Well, we could just not heat Boston for 5 days. Should we just do that? Not an option, right? Sometimes engineers were like, it's 5% of the time, it's 2% of the time. We just won't worry about it, right? I like to say we're engineers, not scientists. We get to do that. But in this particular case, not an option. We have to provide that heat all the time. But the peak ratio, right, the highest to sort of base, right, being so much higher on those 5 days is a huge problem. Okay, so utilities, the folks who provide you with electricity need to really think about this. We all need to be thinking about this. What are we going to do? Because they have got to be thinking about those 5 days. And now there's all this other complexity on the grid as well, right? So your home, for better or worse, is smarter, right? Maybe you have a thermostat that can be controlled by the utility. Maybe you can control it as well to go up or down in terms of temperature. Maybe you have some renewable energy both on your house. Maybe you buy specifically, you pay a little bit more for a utility to supply you with some green energy. That's an option. We've got the utilities really thinking about really this thing, distribution intelligence. So before it was pretty simple. There was a central power plant, And the electricity was generated there, usually by burning some kind of fossil fuel. And then it was sent out to all the buildings. Now we have some central, of course, we'll still have that. But now you've got solar panels on your roof, right? Maybe there's some community hydro. Maybe there's some community solar. Maybe there's some wind nearby, right? And so the solar is dependent on when the sun is shining. The wind is dependent on when the wind is blowing. And you're plugging in your electric vehicle. Everybody's plugging in. That's a huge load on the grid that they never had to deal with before. So utilities are really nervous. They're really nervous about this additional complexity as well as the additional load that we're going to see in the future. So how do we solve this problem, right? We've got to go figure this out. We are engineers. We're going to solve this problem. I have full faith that that will happen. In part, this problem will be solved by looking towards energy storage. So that means using batteries, but as shown here, it means also using other types of storage. So we could, during times when the wind is blowing and the sun is shining, we have all this electricity flowing. Let's use that to pump water. This is done sometimes with compressed gas as well. But we could pump water essentially uphill. So we're going to use the electricity to pump water uphill. And then during those 5 days a year, we'll let that water fall down and kind of get our free hydro, if you will, electricity from it when we need it. So a solution like that, or a solution like putting electricity during these times when the sun is shining and the wind is blowing, putting the electricity into batteries is another option as well. A lot of systems, you might be surprised to know that a lot of solar systems on homes, when they overproduce electricity, it depends what state you're in, sometimes you can sell that back. In Massachusetts, you can sell it back to the utility. In some states, you cannot do that. And the electricity literally goes into the ground. So it's wasted. So we need to do a better job to figure out when there is overproduction, particularly from renewables, what we do with it, how we store it, and then how we deal with all this complexity on the grid to balance it. So what happens sometimes is that, and what will happen more and more in the future, is that you've got a home using electricity, and it's being charged 13 cents a kilowatt hour. That's fine. That's a pretty good price for electricity these days. But when everybody gets home from work and turns on their ovens and their dishwashers and plugs in their electric vehicles and all the lights are on, right, and the kids are watching TV and all those things are happening, what happens is you end up with electricity, that's the red line here, usage, that is above the available electricity that the central power plant, maybe plus your own solar, can give you. Right? So oftentimes if you've been in a brownout, right, that's sort of what happens. More people are asking for electricity than we can give them. And so we have to reduce essentially the voltage for everybody so that we can try and do the best we can to deliver that electricity. So that's what utilities do. So what happens in certain parts of the country, and will continue to happen more and more, I believe, is that once we start getting to a place where it's looking like the electricity demand will be higher than what's available, then the utility will start charging you more for electricity. And we've seen this happen in a very sort of organized way. And California has a whole system to try and deal with this. We've seen it happen in places like Texas when they had a really bad winter for a very short amount of time, and electricity prices and fossil fuel prices kind of went through the roof and caught people off guard. So we're still figuring out how to manage that. And you, as a homeowner, will want to know how to do that too. I'm imagining you're paying 13 cents a kilowatt hour. you're not going to want to all of a sudden start paying 50 cents a kilowatt hour. You're going to say, no, 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 I'm sure we can turn things off in the house. We can change the thermostat a couple of degrees. I don't need to charge my car right now. I'll just wait until 3 a.m. Right? There are things we can do to try and mitigate this issue. So that ultimately what the electricity load looks like is what's shown here. That there's a level of control such that the available electricity can actually meet the demand. I thought I'd throw in something here about the startup company that Dean Lee mentioned. So Edifice Analytics is a startup company that I started with some collaborators at Case Western Reserve. And essentially, one of the things that the company does is take electricity data, right, that you're sending to your utility anyway, and through a data analytics and sort of AI analysis of that data, kind of figures out what might be going on in the home. So an example is Starbucks has been a partner of ours, and they give us 50 data sets, right, of their whole building electricity use. Right? So what their electricity usage is in the whole coffee shop, not on individual things, but in the whole coffee shop over the course of a year. And because of the work that we've done, we can then pull out what the refrigerator uses, what the ice maker uses, and tell them what that load is. If they needed to, if they wanted to, they'd have to go in and sub-meter out the different refrigerators and ice makers in their coffee shops. They could do that. That would cost money. They could send in somebody to do a physical energy audit. They could do that. That would cost a lot of money. Or they could just give us their data and we can tell them what's going on in their building. So Starbucks is very committed to sustainability, for example. And so they're very interested in knowing, are there coffee shops that their refrigerators and ice makers are using too much energy? Right? And those are the coffee shops they'll want to go in and replace the refrigerators and ice makers and put in ones that are much more energy efficient. And so we can do this. We're using more of this building intelligence to be able to gain insight to a building. And you can imagine that's sort of to do a virtual energy audit, now using that same kind of insight, that data insight, and using machine learning to then actually be able to optimize for that complexity I was talking about before, right? Right? Wouldn't it be great if you didn't have to think about the fact that you might be charged for peak prices, and instead you have a system in place that's managing for when the solar goes to the battery, when the solar goes to your house, when your electric vehicle actually gets charged, when it doesn't, when the dishwasher runs and when it doesn't, right? That your thermostat might go up a couple degrees, might go down a couple degrees. You set the parameters, but the system itself, using intelligence, can go in and actually manage that for you. So going back a bit, though, we're still kind of stuck on this idea of those 5 days a year in Boston and how we deal with them. And I don't have all the answers for you. I do know we aren't going to make the grid 4 times as big just to deal with those 5 days. So we got to think of some creative solutions here. One here I'll put out here is, well, we might need some backup fuel just for those 5 days. I don't know, maybe we leave the natural gas furnaces still hooked up just to run occasionally. You don't have to put in as big of a system maybe if you have new construction, but maybe we decide it's okay to burn fossil fuels for 5 days a year to heat our Boston homes and buildings. Or maybe we say, no, this has got to be a zero carbon solution, and we've got to burn something else, right? Because it's probably not electricity. And so maybe that's a biofuel or a synthetic fuel. And the picture here on the diagram is actually burning hydrogen. And I have an op-ed coming out on this soon. It's a little bit of a wacky idea, but this idea that if you can generate some clean energy and go through an electrolysis process and create hydrogen, then that's clean green hydrogen. and actually deliver that to a home or a building. This isn't unlike what happens in some parts of New England, like where I am, where there's delivery of propane and delivery of oil. We don't have natural gas. So delivery of hydrogen, not a huge tank, just one for 5 days a year, that then connects to your system and can then be used, right, on occasion for that backup heating, right? Hydrogen's very expensive. There's a lot of effort to reduce the cost of hydrogen, and yet at the same time, on those 5 days, I think we'd be willing to pay for it. Okay, I'm going to end by saying that, Bill Gates, who was mentioned, I did some work for Breakthrough Energy Ventures as a technical advisor here there to really look at startup companies that had the great potential of mitigating climate change, and amazing people doing amazing work. And really at the end of the day, as Mr. Gates says here, right, this isn't easy. Right? This is going to take many students who are learning these concepts today, who turn into workers in the workplace, who are thinking about energy, who are thinking about technology, but who are also thinking about economics and policy and all of these things, to be able to put that all together to really have an impact, a kind of impact, to solve a lot of these complex problems that we talked about today. So with that, I'm happy to take any questions that you might have.
I don't have a cool, sorry, walk around, right? So I have to use this mic. So thank you, Alexis, for a wonderful lecture. A lot of inspiring, challenging stuff and the things you discussed. I want to kick off the Q&A with a pre-submitted question, if I may. So the question was submitted ahead of time based on the topic of your talk. The question is, in implementing some of these measures you discussed today in auditing in a meaningful way, the utilization of different components, whether it's for heating or cooling or appliance use, what might be an opportunity? So when do we, if we need to install new heating and cooling systems, like what are some opportunities in the way we design over the life cycle of a building where you can do this in an efficient way where the upfront cost is not too high, but you have still meaningful impact on how we utilize it?
Sure, yeah, great question. And I remembered I actually had one more slide, which relates to that question. This is my house in Hanover that we built and moved into in 2021. It's an all-electric house. People, I tell that, they kind of go, what? What if the grid goes down? What are you going to do? But it's okay. When you're doing new construction, right, there's no question you should be thinking about these things, right? New construction is the best time to really think about energy and energy efficiency, and to really spend the extra money if one can. There's great rebates and policies out there, particularly through the Inflation Reduction Act, which is the biggest climate bill that this country has ever passed, but nobody knows that because it's called the Inflation Reduction Act. But so lots of opportunities to take advantage of that. When you're talking about a retrofit of a building, you gotta ask the question. You probably have to bring in some people who can help you navigate. How old is this system? What are the benefits of maybe changing out the system and putting in a new system if it's not broken yet? Is it still better for me to do that? I guarantee you a 1970s, 1980s refrigerator, it is worth the money. The payback is probably 18 months. So please go tell everybody you know with those old refrigerators that they should swap them out because they're paying more to run them than they should, and it's bad for the environment. So it's really an investigation. I mentioned Edifice Analytics, right? This is sort of one of the reasons that we got motivated to do what we do. Is it's really hard to know what to spend money on, what to invest in, particularly in old buildings. And so being able to do some kind of analysis simply, quickly, to have insights to that, to know what to change out is important. But unfortunately, the answer depends depending on the building itself. Yeah.
I may have to follow up with some offline questions. We actually debating this morning, my wife and I, to heat pump or not to heat pump.
Okay, well, let's do this.
So, yes.
So how old's your house?
Let's see. Oh, that's good. 101 years old.
Okay.
It's an old house.
What's the state of the insulation?
It's a part of the house, excellent, because we did some part of the house, I want to say 8 years ago. So
Okay.
it's the sort of fillable foam insulation,
Okay.
so it's pretty good.
Okay.
But third of the house, not so much.
And why haven't you done the rest of the house?
Oh, it's a good question. It's called what we budgeted for the renovation.
Okay. All right. So here's the thing. I would say that you got to do that first before you go heat pump. Because at the end of the day, you're going to have to put in a bigger system because you're going to have a lot of heat loss through that one part of the house. And you don't want to put in a bigger, so you're going to spend more for that system. And then the operational cost, I would say you want to make sure you shouldn't go heat pump unless you feel pretty good that the insulation of the whole house is good enough. So that would be my recommendation.
Thank you. And I'm going to tell my wife.
Tell your
from
wife.
an
Tell your
expert. She said, what do you know about home heating?
Yeah.
And I was like, well, I
Yeah.
don't, but I
Yes.
heard from someone who's an
Yes.
expert, so thank you.
Yes, absolutely. Insulation can be
Insulation first. Got
expensive,
it.
but
Okay.
that's what I would suggest.
Okay, enough about my house. Any questions from the audience?
Yeah. Absolutely. So the question was about stoves, and especially maybe for backup heating. Is that a good option? So absolutely. So wood is a renewable resource, right? We use it. The carbon dioxide is emitted, but then as soon as we're growing another tree in its place, right, we're absorbing that carbon dioxide. So it is a renewable resource. The issue with wood is that for some forests, for some types of trees, right, it might take 30 years before, right, we're absorbing that same amount of carbon dioxide that we just released in seconds, right, into the air. And so if this were 20 years ago, I'd say, yeah, absolutely. Let's go wood. I think we are at a point, unfortunately, with respect to climate change, that we kind of can't wait to get that carbon absorption over that time period. Now, there are fast growth forests, right? There are some trees like bamboo, things like that that you think of that grow really fast. There are some more trees used for like wood pellets that are planted to grow fast. So it's really a question of, I would you sort of have to do the math around how fast are they growing and how quickly how much CO2 are we emitting into the atmosphere when it's burned. So I'm not a huge fan of wood pellet stoves today. Of course, it depends where you are in the world. Access to resources is really important too. As backup power, sure. We're talking, again, if we're talking about a Boston house and it's 5 days a year, I would say that's certainly better than trying to deal with this grid problem that is pretty untenable.
Okay. Irene?
So, thank you. This is very fun. Anyways, outside of my area of expertise, which is medicine, so I'm going to start there. We, as engineers, we develop technology that can disease diseases perfectly, but then they don't make it into the clinic because insurance doesn't make money, or insurance doesn't cover it, or the economics are not there. When we think about technologies like this, or how ultimately technologies that we develop to improve these challenges come about, are there going to be barriers to, or what are going to be
Yeah.
barriers
Yeah.
to having them adopted?
Yeah, the question was really major barriers to having technologies adopted. So most of the technologies that are available today are cost effective. What does that mean? that means if I pay $500 for a new refrigerator, right? And let's say I got rid of my old refrigerator, and I am now spending less, let's say half of the amount that it costs to run that refrigerator than I was with my old refrigerator, right? And that payback, right? If I add up all of that amount that I'm saving every year.
We have a lecture here now.
Oh, okay. Okay.
She's got.
I'll finish up. But so if you add that up, and let's say that your savings you can make back in 3 years, but your refrigerator is going to last 10, then it's cost effective to do that. The question is, do you have $500 to pay up front for the refrigerator, or are you gonna buy the $300 refrigerator because it's cheaper at Home Depot, right? And so that won't pay back, right, in the same way. So things are cost effective. The biggest barrier is the upfront cost to them, because they're usually more expensive for the more energy efficient solutions than the lesser ones. And so there are a lot of programs out there to help homeowners especially, but building owners, even campuses, get the upfront costs paid for, or at very favorable interest rates, so that you can still take advantage of the payback. So they are cost effective, but the upfront costs are really the challenge. So yeah. Are we getting kicked out?
It sounds like that was the last question.
That's right. That's right.
Yes.
So,
Thank you so much,
thank you.
Alexis.
Appreciate being here again. Thanks.
I do have a small token of appreciation. Do we have
Oh.
time to do that, or? Okay. So thank you for that. So as a small token of appreciation, but heavy, small but heavy.
Okay, in proper colors.
In proper color,
Yes,
absolutely.
yes, here we
And
go.
those are blue dots. I
Okay,
believe, so thank you
thank
for
you.
wonderful talk.
Appreciate it. Okay, all
Thank you
right.
so much,
Thank you.
Alexis.
All right.